All right. Um, for starters, uh, some of you maybe already got the emails me requesting it, but when I went to grade the second homework assignment, a whole bunch of you have your Google Colab set up where it's private. So you've given me a link to something I can't access. So either make it public or um, just invite me as a collaborator. And the email address I use on there is that. So one of the two. Just make sure I can view the code. I don't need to even change it. I think I probably requested edit access, but I don't care. Make sure I can see it. So at this point, some of you have grades for those. I didn't give a 0 if you had a bad link. I just requested it and pretended like I didn't grade it. So you'll still see some things ungraded. If that's you, if you see something ungraded, you need to go back in and give me access. Got it? All right. It won't be late or anything. Just get it figured out now. So the next homework assignment, we don't have the issue because pretty soon here we're starting to angle into actually writing code, maybe even starting today. There's assignments are going to get more serious. All right. So and of course, I got my ridiculous slides that are all over the place. Wow. Just look at it in code here. All right. So I created some variables. Last time we were talking about this idea of a pointer. We've been talking about loosely typed versus strongly typed programming languages. What's the difference between a loosely typed and a strongly typed language?
Made the same idea with less versus like a loosely typed, you have to kind of explain code all of it, like assembly versus Java in a sense.
That's high level versus low level. Go ahead.
Oh, loosely types mean you don't have to specify variable types, while strongly typed is when you have to specify each variable as it's created.
Yep. So remember back, we had one of the early slides, how do human beings solve problems? We remember stuff, we ask questions, we do repetition. 100% of programming languages have facilities for those three things. Loosely typed versus strongly typed deals with the idea of remembering things, creating variables to store information. A loosely typed language like Python does not require us to label a variable for the type we're going to put in there. Python does allow that since it's being used for higher performance stuff now, but it doesn't require it. Whereas strongly typed languages, Java, C#, C++, C, they require you to put right here, the type before a variable. So these 4 lines right here, I'm creating places to store stuff in memory. I'm putting values into memory somewhere through variables. So these 4 lines are an example of the first way humans solve problems. We remember stuff. And because I'm dealing with a strongly typed language here when I'm in C, I have to put the type. So that's an int, integer. That's a long. And we've talked about these. An int is a 32-bit signed integer. A long is a 64-bit signed integer. Here's an int. What's this guy? We talked about it a little bit last time. What I have highlighted. Int star. What does int star mean? Pointer. What's a pointer? Okay. So would you say that you found it hard to describe what it is?
Yeah.
So let's make it so it's easy to describe what it is. What kind of value does age hold here? An integer, a whole signed number. What kind of value does age 2 hold here? A long, which is another whole signed value, but can just hold bigger ones, right? This is another integer. This guy right here is an int pointer, which means it holds memory addresses. That's it. All the other ones held whole sign numbers. This one holds memory addresses. Just remembering a thing in case I need a memory address for some other reason. When we say we're going to remember something, we're not necessarily dictating how we're going to use that. We're just saying, I need to remember something. Sometimes remembering memory addresses is important. Go ahead. That's the, well, we're actually going to be talking about that here in 30 seconds. So ask again in 5 minutes if it still doesn't make sense. All right. In fact, let's just jump into that. When I say address to you, move your mind outside of computers. When I say, what's your address? How would you probably answer that? Go ahead. Yeah, maybe it's your home address. Maybe it's Concordia's address with your dorm number or residence hall number, whatever they call them this year. You know, for your Amazon deliveries or something like that. You know, you have these addresses, right? Now, what goes into an address? You have street number, you have a number, you have a street, right? You have a city, you have a zip, you have a state. Keep going, you have a country, right? Probably aren't putting our planet on there, but you could, right? The point here is that, and are any of you intimidated by addresses? When somebody says, what's your home address? Do you start like getting the sweats like, oh, this is a hard one. I can't remember it. Or do all of you know what your address is? It doesn't seem like an intimidating thing, does it? Yet, we just covered that you're having to remember a whole bunch of pieces of information. You know, I remember the very first house I lived in Rantoul, Illinois. You know, the whole rigmarole. I got all these things memorized that they made me memorize. I don't know, as a kindergarten, what do you memorize your address? As soon as you're mobile enough that you need to be able to get home if you get lost. But we've been doing that our whole lives, yet our addresses really are pretty complicated. Now, a memory address is the same thing. It's where is something located. It's just our computers' memory addresses. Think of our computer's memory. You have 64 gigabytes of memory, 32 gigabytes of memory, 16 gigabytes of memory, whatever your computer has. Think of that memory pool as kind of like a town. Okay? So if you have more memory, bigger town. All right. There's more addresses in Milwaukee than there is in Grafton because Milwaukee's a bigger town. All right. But in a computer, all the houses are on one street. You don't have this idea of a street name, a city name, a country, all these extra things. All you have is a number. This is house 0. This is house 1. This is house 2. This is house 9. This is house A, B, C, D, E, F. This is house 1A. You're counting in hex. We happen to use hexadecimal values to count these houses. Now, let's just do a little math for this just to put it in perspective. You know, I really kind of hate these slides. My homework for Tuesday is to go through and basically delete all the stupid slides. Okay. If I don't submit that by Tuesday, everybody gets extra credit. So hold me to that. Because I can't find where I put crap. I'm that absent-minded professor mentality. I didn't even know what I was talking about when I walked in today. So in any case, let's do, I'll just add a random slide since I don't know where I am anyways. So let's think about the number of addresses that we have. So what would be considered a reasonable high amount of computer memory today? Maybe 32 gigabytes?
RAM.
Yeah, RAM. 32 seem high, but common. People have 32 gigs of RAM, right? All right. So more so than have 64 or 128. Most people probably have 16. Probably your sweet spot with some 8s, but let's just say 32. So I have 32 gigabytes of RAM. All right. That's the size of our town. All right. So This is the size of our town on our computer when considering addresses. All right, now we're going to keep this simple. We've talked about various data types and how much space they take up. Let's just think about this in terms of integers. So the question is, how many ints can fit in 32 gigabytes? Take 2 minutes, solve that problem. You have all the knowledge that you've learned in this class so far to answer that question. How many ints, that is 32-bit values, 4-byte values, 32 bits, 4 bytes mean the same thing? That's how big an int is. How many of those will fit inside of 32 gigabytes of memory? So try to answer that and look through your notes. We had the charts and stuff, then we'll solve it. All right, so let's look at this. We know an int is 4 bytes big. Let's just work in terms of bytes. So how many bytes is 32 gigabytes? So 32 gigabytes is times 1024. That gets us to megabytes times 1024. That gets us to kilobytes times 1024. That gets us to bytes. So we have this many bytes in 32 gigabytes.
4 bytes is 32 bits.
Yeah, 4 bytes is 32 bits. 32 divided by 8. So that's how we get from bytes to bits.
Alright.
Gigabytes, megabytes, kilobytes, bytes. So I went from gigabytes times 1024 got me to megabytes, times 1024 got me to kilobytes, times 1024 got me to bytes. So I took 32 times 1024 times 1024 times 1024, and it gave me this number right here, which is the total number of bytes in 32 gigabytes. So this number and this number mean the identical thing. I'm just expressing it using 2 different ways. One's in bytes, one's in gigabytes. All right. So now we want to know how many there are. So I'm going to take that. Now I'm going to divide it by 4. And this is, well, can I get it from there? Oh my gosh, I suck. All right. So that's 8,589,999,999 934,592 integers that we could potentially store inside of 32 gigabytes of RAM. Now you got to consider your operating system takes up some memory and stuff like that. But if we just keep it clean and say, I got a bucket that can hold 32 gigabytes of stuff, I can put 8.589 billion integers in there. A lot of integers. How many of you think you'll ever write a computer program that needs to remember 8.5 billion different numbers? Unlikely, right? So we have tons and tons and tons of RAM nowadays for storing stuff. Now, just to throw it the other direction, let's go back in time. What was that? Have I ever seen that one before? Whatever. So remember we had the, on another slide, I had the famous Bill Gates quote, you'll never need more than 32K of memory. So if we take 32 kilobytes of memory is what he's talking about, bytes. How many ints? So 32 kilobytes is 32,768, or 32 kilobytes is 32,768 bytes. And we know an int is 4 bytes. So 32,768 divided by 4 is 8,192. All right. So that kind of takes us back into the mid 80s or something like that in terms of what was considered a large amount or a big amount of memory back in the 80s. This would have been expensive, 32K of memory back then. It can hold 8,000 integers. Now, how many of you think you'll ever write a single computer program where you need to remember 8,000 unique integers? Probably still unlikely. Once you start getting into collections of things, maybe. But certainly seems much, much, much more likely than ever needing this many integers, right? All right, so that's what computer memory is holding. Go ahead.
On that one, we divide by 4 because int is 4 bytes.
Yep.
Okay.
Yep. Yeah, so an int is 4 bytes, which is the same as 32 bits. You could just decide how you want to express it. Since all of our memory is typically measured in bytes, it's usually easiest to think about it in terms of bytes. But if you had gone into Best Buy years and years and years ago when, in the kind of the early days when computer hard drives started getting bigger, they would usually give you the size of the hard drive in terms of bits. Why? Sounds bigger. You got 40 trillion bit hard drive. The zeros get truncated off the thing. It's like, man, I'm never going to fill this thing. When it probably like a 420 megabyte hard drive or something like that. All right. So this is kind of what we should be thinking about when we think about computer memory is how much stuff can I store in there? And now we just kind of thought about it in terms of an integer, which is kind of our average number that we store. And since we've been talking in here, most of the stuff that we want to store is numbers, one way or another. All right. So now we're talking about our town, right? Where would I put that? So bad.
I think you just skipped.
Oh, here we go. All right. So if we assume we have a computer with 32 gigs of memory, 32 gigabytes of memory, that's the size of our town. Our town can have a population of 8.5 billion integers, if we want to think about the extreme, right? That's the number of tiny places there are to live in our 32 gigabytes of memory, okay? But this town is nowhere near as complex as the towns that we're used to. Even in a small town like Mequon, you have your street number, your street you live on, Mequon, whatever. So, there's multiple pieces of information that ultimately tell you where something is. In a computer, every single house in that town lives right next to each other. You don't have to keep track of the street name, the town name, city, or state, whatever. You don't have to keep track of all those things. It's just this is house one, this is house two, this is house three. Big, big, big long street. So memory addresses are just numbers in a sequence. They're actually representing something very, very easy. So now the question is, why use hex for memory addresses? So if we were talking about this using our number system, which is not intimidating to us, right? As soon as things start having A's and B's in it and somebody tells you those are numbers, you start freaking out, right? Okay, but our number system we're comfortable with. So this is house 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, blah, 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 all the way up to 8.5 billion, all right, for 32 gigs of RAM. Now, what if we were counting in binary? This is house 1. This is house 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You got it. Once we get down to that 8.5 billion, we have a good number of zeros and ones next to each other. That is a big old number, right? Even though it means the same thing as 8.5 billion. All right. Why do you think we use hex for memory addresses? Yeah, smaller footprint. Okay, they have a smaller footprint, so we can represent relatively large values in smaller pieces. So we can take that 8.5 billion, and if we turn that into the hexadecimal equivalent, it'll still be a big number, but it's going to be a much more palatable number. If I was going to take 8.5 billion and turn it into from decimal, and I wanted to convert it to hexadecimal, which of the two patterns would we use? The divide one, right? So if I have 8.5 billion in decimal and I want to convert that to hexadecimal, I would divide it by 16 over and over and over again, recording the remainders, right? So if we cheat on this real quick, 8, well, here, let me grab my actual number. That's that number in hex. Yeah, it doesn't look that, we don't have the A's and B's, so it doesn't seem as bad, but this is the space 16 representation of that. So this guy has 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 hextets to represent that value. This guy up here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I may have miscounted by 1, but more. More digits to represent 32 gigabytes, the largest address we can have. It takes more digits than we can use than it takes to represent it in hextets. All right, that's why we use hexadecimal. Now, why specifically hexadecimal instead of base 17? Because wouldn't base 17 potentially be even shorter? Base 18 be even shorter? Base 22 be even shorter? So why are we picking base 16? No, I think you're you only said one word, and I think you're right. And so what does everybody else think? Why did we specifically So we've already answered the question. We've picked hexadecimal over decimal because hexadecimal the memory address will be a smaller footprint, take up less physical space. Doesn't need 2 seats on Southwest. All right. So why didn't we pick even a bigger base than base 16, like base 22? Because that would make it even smaller. Why not? Why base 16 instead of base 22? We've also talked about this, but hopefully you're seeing that we're talking about a whole bunch of stuff and then we just start connecting them together. What is nice about hexadecimal when it relates to moving between binary, which we know that a computer speaks, and hexadecimal? Is there a convenience of binary to hex that makes moving between binary and hexadecimal easy, as opposed to having to go binary to decimal and then decimal to hex? We can represent the entire hexadecimal, all the hextets, 0 through 9, A through F, we can represent those as 4 bits. So we can move between hexadecimal and binary directly. All right, so we don't need to do that middleman conversion. We don't have to take a number to decimal first and then convert it to the other one. All right, we can just directly move it. If we wanted to go larger than hex, then we would need to go to the next value up, which is 5 bits to represent the entire value system, which would be 20. Is it base 36? I think base 36, but you can do the math. 5 bits. 5 bits is the representative. We're not quite at that point. You know, maybe if we fast forward a bunch of years, if the amount of RAM we're talking about in our computer is, you know, 256 exabytes or something like that, maybe then our number of addresses gets so large, they're like, you know what? Base 16 really isn't cutting it anymore. It's still pretty scary. These are how big the hex numbers are. So, but we'll have to jump up to a much larger base so that we can work within the convenient moving between binary and base 36, because it'll have all the values can be represented in 5 bits. Whether we get there or not, who knows? Go ahead.
Can you give an example of like a binary? I don't remember exactly how.
Okay. Yeah. So let's see. Let's pick our favorite binary number. All right. There's my favorite binary number. All right. So that guy's in binary. Now I've mentioned that and we want to convert this to hexadecimal. So because we can represent each hextet in its entirety with 4 bits, we want to break this into 4-bit chunks. And then we'll pad that far left one to get it to full 4 bits. All right, because 101, this guy right here, is the identical value as 0101. All right, 0 times, this is the 1's place, the 16's place, the 256 place, the 4096 place. 0 times 4096 is still 0. All right. So to convert this, what we do is we take each 4-bit chunk and we take it from the binary number to its hexadecimal equivalent. All right, so this is the 1's place, 2's, 4's, this is the number 5, right? 0101 is the number 5. Everybody good with that? 0101. This is the 1's, 2's, 4's. This is the 8's place. This is the 4's place. This is the 2's place. That's the 1's place. So we're using that pattern where we do 8 times 0 plus 4 times 1 plus 2 times 0 plus 1 times 1. And that's going to give us 5. All right, so everybody's understands how we can convert those 4 bits from binary to, we're converting it to hex, but right now we can think about it as decimal, doesn't matter. All right, so that means that what we have here is this is the number 5. What's this guy? This is the 1s, 2s, 4s, 8s. This is 8 plus 4 is 12 plus 1 is 13. This is the 1s place, 2s place, 4s place. So that's another 5. This is 1s place, 2s place, or 4s place, 2s place, 1s place. So this is another 13. All right, so each of these 4-bit chunks represents these values, 5, 13, 5, 13. Okay, an A is a 10, a B is an 11, a C is a 12, a D is a 13. So this is 5D, 5D. That's the hexadecimal equivalent of that binary number. So 4 hextets wide compared to however many zeros and ones this is. This is 4 times 4, 16 minus 1 is 15 since we added the 0 on the side. Now, something I'll throw out there. Obviously, moving between all these numbers and stuff like that is still going to be weird for all of you, right? And the reality is that as a computer scientist, you're not going to be having to do this as part of your job. But it's important that you understand this is what's happening under the hood. All right. So I know I'm moving between numbers and I've been doing this for a few minutes. All right. I want you to get to the point where you kind of understand that the base is just like a different language. It's like saying the same sentence in Spanish versus English versus French. I can say the same number in binary, in decimal, and in hex. Okay. It still means the same thing. And ultimately, we're putting stuff into a format that is most convenient for computers and us to collaborate with. Make sense? So we've specifically picked octal, base 8, because all the octets can be represented in 3 bits. We've picked hexadecimal, base 16, because all the hextets can be represented in 4 bits. So we don't have to convert between octal and hex back to decimal before we go to binary. So it's convenient to just get to between binary and those bases. Make some sense? That's the rationale of why we picked base 8 instead of base 9 or base 16 instead of base 18. All right, because it just is convenient. It's the math works. All right. So as we're trying to understand this guy that we want to be able to tell what to do, we want to think about, okay, in what situations are we using hexadecimal? In what situations would we expect to see things represented in hex? Probably in situations where there's a whole bunch of numbers that we're trying to represent, and it's going to be a whole lot more understandable. It might be a little uncomfortable because you're not used to looking at hexadecimal values. Start seeing alphabetic letters and stuff like that. It's uncomfortable. But whenever we need to represent a whole bunch of different values, hex is probably our go-to move as opposed to the other extreme looking at 4 zillion zeros and ones, which means the same thing. Make sense? So this 0 and 1 thing is as far from human comfort as we can get. Now, we could say, well, why don't we just represent it in decimal? Well, because moving from decimal to binary is more complicated than moving from hex to binary. Hex to binary, we can just do that direct 4-bit mapping. Decimal to binary, we have to do that divide by 2 over and over again, recording the remainder and read it from the bottom up. It's doable. It's not the end of the world for us, but it does take a few minutes, right? All right. So hex, when we want to represent a really long list of things. Octal, we don't have a good example in here. It's used a lot for file permissions and file systems and things like that. But We can appreciate that the reason they picked octal base 8 is because of it's just like hex. It could be done in 3 bits instead of 4. Going to kind of appreciate that reality. But octal, from our perspective, is probably the thing we're going to see the least often. At some point when we have an example of it, I'll point it out. It's used for file system permissions. It's used for masking. Unimportant to you at this exact moment, other than just that its relationship to bits. All right. Binary, obviously, computers speak zeros and ones, ons and offs. Okay. And decimals, where we're starting from, this guy's starting from zeros and ones. We have to be able to move between us and that guy relatively conveniently without us having the 2-button keyboard. So we need to make programming, telling a computer what to do, as convenient as possible for us as humans, because it would be we'd be very error prone otherwise, right? It's not our cup of tea to be super, super precise, tapping out 4,000 zeros and ones. We'd almost definitely make a mistake, right? I'm making mistakes counting seven bits, 13 bits, whatever it was. All right. Questions about that? Did that kind of answer your, I know you asked the question about memory a while ago. Does that make sense?
Like, I would like someone like want like what's like why would someone specifically use like the memory address in their code instead of just like doing like the
Yeah, they wouldn't. The reality is, if we're writing the code, there is probably a world somewhere, probably virus writing or writing hacking tools for crack video games or something like that, where you might embed actual hexadecimal numbers in your code. But for all intents and purposes, let's just say that doesn't exist. Nobody does that. So who's bringing the hexadecimal values into the world? It's going to be that interpreter for Python, or it's going to be the compiler for strongly typed languages and strongly typed high level compiled languages like C, C++, Java. So that middleman that sits between us and the operating system, it's going to go out and request, when we say int a equals 7, it's going to go out and talk to the operating system on our behalf and say, I need a place to store this number 7. I want you to label it with an A because that's what this human says they're going to remember it as. But give me the memory address where you put it and I'll take care of the rest. We had to force the program to show it to us. I wrote that code last class where I had to kind of do I have a whatever. Yeah, this code last class where this is not a hack, but I had to do something special here in code for it to ultimately show me hexadecimal values. Chances are when you're writing a normal program, you would never see hexadecimal values unless you were purposely trying to look at them. All right. So when you're coding, you don't have to think hex. You don't have to think binary. When you're coding, you think in decimal, which is what we're already comfortable with. If I want to store a number, I'm going to write the decimal version of that number because we're comfortable with that. Ultimately, that number is going to get stored in the computer as zeros and ones. So that hex or that octal is the translation between those two, but it's handled for us by this software layer that sits between us and the hardware of this computer. All right. So you might go through your entire career and never write a hexadecimal number once. But it's still important for us to understand that when we're talking to this guy, there's a reason for these things, because every now and then you might have to deal with bits or with hex for very specific problems. So we'll call that, this 5% outlier problem that you might only sometimes run into. But it would be in high performance computing stuff. So video games, maybe some AI stuff where you are purposely hard coding values to get just as much performance as you can out of something. Does that help?
I
think so. So I feel like that, like, and star, like, is that something that, like, doing?
You would if you were a C programmer. So what we're looking at here is a language from the 70s. And most of our modern languages have taken this special syntax that's right there, have taken that out, and it just says, don't worry about it, I'll handle it for you. If you want to put it in context, this is driving a stick shift car as opposed to an automatic transmission, where it just does the shifting for you and it just says, you don't have to deal with this. So in here, since we're going to be using Python, you won't have to deal with, there isn't a syntax for directly saying, I'm holding a memory address. What other happening is we'll create instances of objects, which I promise you behind the hood will be stored as memory addresses, but it's not your choice anymore. All right. Okay. So I'm just going to create this slide again. How do humans solve problems? Memory, asking questions, repetition. That's how we solve problems. 100% of programming languages, I call this the mapping, have facilities for these three things. Memory is through variables, which you've already been experimenting with in your code, your assignments. Asking questions are through conditionals, usually if statements. And repetition is done through loops and functions. All right. Every single programming language gives us facilities for these three things. So what really the punchline is that every problem we ever solve on a computer, every single time we tell this guy what to do, we have to explain it to it in terms of these three things. We tell it, what are all the things we have to remember? All right, now we're going to ask some questions about those things. And the answer to those questions is important for what do I do next? Just like real life. And then a lot of times we're going to be doing that same pattern of stuff over and over and over again. All right. All right. So before I move forward, do we understand that variables like int a equals 7, that's how we remember stuff in our computer programs. All right. In Python, we would just say a equals 7. We leave the int off because it's a loosely typed language. The syntax is not that important. You will learn the syntax of these programming languages just by doing it. So don't sit there and try to memorize it. You're going to put in the reps, you'll remember the syntax. So programming is the skill set we're chasing. Thinking about how can I describe what I want this program to do, what I want this computer to do in terms of these three things. All right. So we're going to ask some questions here, and we're going to have some loops here. All right, so now convert let's take our knowledge of converting 1010 from binary to decimal, and instead of doing the math, just giving me what the final answer is, let's try to describe how we're going to solve that problem in terms of remembering stuff, asking questions, and repetition. All right? So take a couple of minutes. See if you can give me step-by-step instructions for how I can go from 1010. This is 2s, 4s, 8s. So this is ultimately this will be the number 10, right? 1010 is the number 10. So I want you to give me step-by-step instructions using only variables, conditionals, and repetition. I'm not asking for Python code. I'm just asking for the verbal steps. Remember that the number you're starting with is 1010. We got to remember what we're starting with. Then how do I ultimately get to an answer of 10? All right, so take a couple minutes and try to express that to me in words.
You don't have to use the map. What you just went over with the map to explain it. It's just literally telling you how we can get.
Yeah, say, remember this, do this to it, do this to it, do this to it. Keep doing those things until something occurs. Then you're done. Show me the answer. Yeah, just very generically. It should be usually this is called pseudocode, what we're writing. But don't even think about it in terms of code. Just give me step-by-step instructions for converting this in terms of those ways that computer programming languages allow us to solve problems. And what you're trying to do is you're trying to take your knowledge of how you can convert this from binary to decimal mathematically, and you're trying to describe that step-by-step process in terms of what do I need to remember, what questions do I have to ask, and is there a group of 3 or 4 or 5 steps that I just keep doing that over and over again until some condition is true? That's what you're trying to explain to me. Convert your knowledge of taking this guy from binary to decimal, turn it into something that is the thought process that a computer would understand. All right. So let's think through this. So the first thing I'll leave that guy there. So first thing I'm going to do is I'm going to remember my starting value. Initial value is going to equal 1010. Remember my starting value. I got to know the thing that I'm trying to convert. All right. Now, if you're converting this guy by hand, when I write the 1010 out, what are we ultimately doing? We're saying this is the ones place, this is the twos place, this is the fours place, this is the eights place. So let me write those out. This is 8, 4, 2, 1. On the far right here, no matter what base we're converting from to decimal, that far right is always the number 1. So in this case, it's 2 to the 0th power, which is 1. If this was octal, it would be 8 to the 0th power, which is 1. If it was hexadecimal, it would be 16 to the 0 power, which is 1. So if I'm always starting off at this far right place, I can say I want to remember place is equal to 1. All right. Now, what happens to place as we go from 1 to 2 to 4 to 8? What am I doing to place each time through this? Multiplying it by 2. All right. So I'm going to do something here. I'm going to take this value, multiply it by that value. I need to store that somewhere, right? So, and so ultimately, as I'm going across here, I'm summing up a bunch of stuff, right? I have 1 times 0 plus 2 times 1 plus 4 times 0 plus 8 times 1. So I'm going to be building up a sum. So when you sum something, we usually start off with 0, right? We have nothing right now. We're going to be adding to nothing, right? So I'm going to have another variable here called sum equals 0. All right. So now what I do is I have a variable called place, and I need to take this 0. So we need to have a way of accessing a specific place in our 1010. Let's not get into the weeds with that right now. Let's just say get the value at a certain position. So this is position 0, 1, 2, 3. So we're going to say pause is equal to 3 as my starting point. We'll make this more generic as we do it, but for this exact example, that's what pause is going to be. It's going to start off at 3 because this is position 3 in my string. This is the 1 is at 0, the 0 is at position 1, position 2, position 3. So there's 4 things in there, and we start counting at 0 in programming languages almost always. And we'll get into the details of that more, but this gets us where we need to go. All right, so I'm going to be building up my answer inside of sum, correct? So the first thing I'm going to do is I'm going to take my current value of pause, and I'm going to multiply it by my current number. So let's just go ahead and say we'll call it cur bit, since this is a binary value and it's a collection of bits, zeros and ones. So we're going to say our first bit we're working with here is this guy right here. So my cur bit is 0. So now what are we going to do? We're going to take my current place, we're going to multiply it by our current bit, and we're going to add it on to our running total, our sum. So this will be sum equals sum plus place times cur bit. Right? So the very first time through, this is going to be sum is equal to whatever sum currently is, which starts off at 0. So it'll be 0 plus my current value of place is 1. My current value of cur bit is 0. 1 times 0 is 0. Add that to 0, should still have 0. All right, so we'll add up our sum there. Now, what has to change with place and cur bit? Before I want to do my next step in the math, I have to update place to be different than it is now. So what do I want to have to happen to place? Place is currently a 1. What do I need it to become? 2. How do I get that 1 to become a 2? Multiply by 2. So I'm going to say place is equal to whatever place currently is times 2. If place is currently a 1, it's now a 2. If it's currently a 2, it's now a 4. If it's currently a 4, it's now an 8. Make sense? What am I going to do to cur bit? We're just going to generically say, make it the next bit over. So we're going to say, what we need to do is we need to change pause to be 1 smaller than it currently is. So we'll say pause is equal to pause minus 1, because now we want the thing at position 2 in there. And we're going to say cur bit needs to be overwritten with a new value. That new value is the element that lives at position pause. So bucket 3, which in this case is a 1. And I'll go ahead and write this. I'm going to say initial value at position pause. I'm going to write it like that, just to kind of give us an idea that we are accessing a portion of that starting value. All right, and for our original curve bit, we could have said that this is initial value at position pause. And a comment in Python is a pound symbol, so this is 0 the first time. That's what we got there. Position pause was position 3. Pause started at 3, and there's a 0 that lives there. All right, so we update curve bit. Curve bit is now a 1. So it's a 1 this time. That little pound symbol with the that just says, don't treat this as code. Just this is like a note to us, a comment. All right. So we just happen to be keeping track that curve bit's currently a 1. All right. So now what do? Don't we actually just keep doing that chunk of code right there? We're going to update sum to be whatever it currently is plus whatever the current value of place is times whatever the current bit is. Make sense? This guy right here and this guy right here are the same line. I'm going to take this out, and what I'm going to do is I'm going to indent all that just so we can see that this is the sequence that we want to repeat over and over and over again. These are the 4 steps that we want to repeat. We want to say, what's the current bit we're looking at in the number? Now let's take the sum times, or take the sum and add to it that bit times our pause. Then we'll update our place to be times 2, the 1's place and the 2's place and the 4's place and the 8's place. So we'll update place, we'll update pause, go and do it again. So now the new version of curve bit is a 1. Sum is equal to 1 times 2. So that'll get us to that 2. So if we're keeping score down here, we'll say sum is 0 initially. So sum is 0 initially. The first time through, we're going to take our current bit is a 0. 0 times our current place is a 1. 0 times 1 is 0. Add to our sum is still 0. Nothing's changed because we added a 0 to it. Then we update place. Place is now a 2. We update pause. Pause is now a 2. 1 smaller than it used to be. So place used to be a 1, and now it's a 2. Where's that off the screen? I thought it was supposed to. All right, good enough. So we have pause. So pause started off as a 3, and now pause is a 2. We subtracted 1 from it right here. Then we spin back up, and we're going to repeat this block of code. So what's the next thing we do? We're going to take curve bit, and we're going to overwrite it. It used to be a 0. So it used to be this far right guy here. But now it's going to be whatever it is, initial value at position pause. So our initial value at bucket 3 is this 1. That guy right there. So curve bit becomes a 1. All right. So now curve bit's set. Then what do? We take our sum, whatever it currently is. It currently is a 0. We're going to add to that whatever our place currently is. Our place is currently a 2 times our current bit, which is a 1. 2 times 1 is 2. And we're going to add that to our sum. 0 plus 2 is 2. Then what do? We multiply place by 2. Place 2 times 2 is now 4. We subtract 1 from pause. So pause goes from 2 down to a 1. We spin back up. We get our next bit. Our next bit is curve bit is the initial value at position pause at position 1. So 0, 1. So it's a 0. Second element in there. So now curve bit is a 0. Now we could throw some stuff in there and ask the question, if it's a 0, just continue, skip this loop through, but the math still works. So we'll just keep it as long-winded, but as simple as possible. So now my curve bit is 0. Then I go and I update my sum. Sum is equal to whatever sum currently is, which is 2, plus whatever place is, which is currently a 4, times whatever the current bit is, which is a 0. 4 times 0 is 0. Sum, which is currently 2, 2 plus 0 is what? Still a 2. All right. So we've updated our sum now. Now we need to update place. Place is equal to whatever it currently is, which is a 4, times 2. So that becomes an 8. Then we're going to update pause. Pause is going to be equal to whatever it currently is, minus 1. So 1 minus 1 is 0. Spin back up. Curve bit is going to be my element from my initial value at position 0, the very first value, which is a 1. So curve bit is now a 1. Then I'm going to take my sum. Sum is equal to sum, current value sum, which is a 2. 2 plus place, which is an 8, times curve bit. Curve bit's currently a 1. 8 times 1 is an 8. 2 plus 8 is a 10. So we've updated sum. Now we'll update place. 8 becomes a 16. We'll update pause. Pause is equal to whatever it currently is, minus 1. That takes me to a negative 1. 0 minus 1, negative 1. Okay. Then I spin back up, but we know that we're done, right? And we should kind of sort of stop at this point. What can you tell me about the current state of the things we're remembering that should raise the red flag that says, okay, you have now completed your task? The negative 1. So we're going to say, keep doing this stuff. Keep doing the stuff below until pause becomes negative 1. Once pause becomes negative 1, we know we've now repeated this enough times that we've collected our sum up to be our correct answer. All right. So finally, once we fall out of that loop, that repetition cycle there, we're going to go ahead and we're going to print the value of sum. Which is going to give us that 10, because the current value of sum is 10. That makes sense? So now we're going to call this our pseudo code. We can now change our initial value to any other binary number, and apply these same steps to it, where pause starts off at our last legal position. So if it's a binary number with 10 bits in it, pause would start off at a 9. If it's got 200 bits in it, it would start off at 199. Then keep walking backwards a zillion times. You definitely want a computer program for that one. Now, you don't want to do that tedium by yourself. But now you can start with any initial binary value, and you can whittle it down and get stored in sum the decimal equivalent. That makes sense? All right. Steal that. So what if I wanted to convert BAD, which we know is 2989 if we were to do the math in decimal. We wanted to convert BAD to decimal programmatically. We use the identical pattern, right? If I were doing this by hand and instead I had BAD, I would start off and say, okay, well, this is the ones place. This is the 16s place. This is the 256th place. So times 16 times 16, because we're working with base 16. Identical pattern, right? So since we know it's the identical pattern, we should feel like, you know what? This code is already probably close, right? We're kind of doing the exact same thing, but because we're working with hex, there's another little complication that's involved here. What complication exists for us when we're working with hexadecimal, or what complication might exist for us when we're working with hex that will never exist in binary? Yeah.
Do we have to assign B to 11? Do we have to like break down the?
The very least, we might have letters, right? If it's binary, we're only dealing with zeros and ones. Those are mathable, right? If we start getting letters in there, now things go sideways. So we need to account for A through F is the idea. All right. So let's go through here. I'm gonna say this is BAD and this is 2989 is what we should get out of that. Ugh, it's too much glare there for my old eyes. All right, so we'll start off our initial value here, BAD. Does place still start at 1? Is the far right element of any number always going to be that base to the 0th power, which is 1? So I don't change this at all. Place is still going to start off at 1. I'm going to be building up a sum. Does my sum still start off at 0? Pretty much every single time you're going to be building a sum up, you're going to start with nothing. So you'll start with 0. If you're going to be doing multiplying stuff, you probably start with a 1 as a good multiplication base. Because if you start it with a 0, then you're never going to get anywhere. 0 times anything is going to stay at 0. All right, so sum will stay at that. Pause. Pause is going to now be, this is 0, this is 1, this is 2. So pause will be the last legal position in my initial value. We'll put a little comment there. So last legal position in initial value. All right. And if you wanted to write this programmatically, you would say this guy in Python. Anybody know what you'd write here in Python? If we just want to kind of add a little bit to the mystery here. If I was writing this in Python, how do I say, give me the last legal value in a string? I don't necessarily expect you to know this, but does anybody already
It would
know?
be like Nick.
Well, I wanted to give me a 2 in this case. So here's my initial value, BAD. So I'm going to say, give me the length, it's usually LEN, of initial value minus 1. So my initial value here is BAD. How long is BAD? 3. Yep. So since it's 0 based, we subtract 1 from whatever the length is. All right. So that's how I got this 2 as my starting point. All right. This is the first bit we're going to be dealing with, except now it's not called bit. It's now called hextet. We just call it value, whatever we want to call it. All right. So I get my position. Now I'm going to keep doing stuff until pause becomes -1. And actually, I need to move this up. So this is the kind of the code version of what that line actually is doing. The position of the far right thing. So now I'm going to keep doing some stuff here. What am I going to do? we'll keep calling it cur bit just so we don't change it, even though it's kind of a mediocre variable name because it's no longer the current bit. It's kind of the current hextet, right? It's no longer a 0 or 1. Now it's a 0 through 9 or an A through F. All right, so this guy is going to be whatever my initial value is at position pause. So the very first time through here, that's a D. All right. So if I come down here and I say cur bit, you know what? Let's change it to hextet so we get into the habit of using meaningful variable names. Because then we'll make this. So initially, hextet is a B. All right, we're good there. All right, so hextet is a B initially. Actually, I'm lying. It's a D, this last value. So cur hextet will be the initial value at position pause. Pause is currently a 2. Place is currently a 1. And we're working with cur hextet instead of cur bit. All right. So now in my current code, I'm saying get me the cur hextet. So that got me the D. But now go ahead and say sum is equal to sum plus place, which is a 1, times cur hextet. And what is the value of cur hextet right now? It's D. 1 times D gives me what? A problem, right? A problem. So we need to add one little step in here that we didn't have before. Because now, and we could have had it before. We could make it, we're going to generalize this as we keep going through here. But for right now, we're going to make it work for hex. At the very least, we need to add a step in here that says convert the current hextet to its numeric equivalent, right? So a D is actually a 13, right? All right, so we'll say convert cur hextet to numeric equivalent, which means that this D becomes a 13. Now I can do my sum step because I can take 13 times 1, giving my current sum is at a 13.
Wouldn't you essentially do like int D equals 13?
Don't worry about the code at this point. We're just replacing. A D means 13. All right. So then what do? I update place. So it's place times 16 since we're dealing with hex here. Pause minus 1. The pause becomes a 1. Spin back up. We're going to get our next value. Our current hextet will be an A, which is a 10. Times 16 is 160. Plus 13 is 173. So that's that next math. Then we'll do 256 times an 11. That'll give us a number. Add to our sum. We'll end up with 2989. All right, so we just added one little question in there. We said, if you are a letter, if you are an A through F, I'm going to replace you with your numeric equivalent 13 through or 10 through 15. Make sense? All right. 2989. Yeah, the final answer here, if you keep walking through there, will be 2989. All right, questions, comments, concerns, bribes. Remember, update your collab so I have access to it so I can go back and grade assignment 2 and work on assignment 3 for, on Tuesday, we're going to be converting this to actual Python. All right, we're going to take our algorithm, we're going to convert it to Python, and then we're going to say, hey, what if I want this to work for any base, not just binary, not just hex? All right.
You know,